Before we introduce the Java platform, how about answering a very basic question? What is a PC? Take your time. The dictionary definition of computer is that it is an electronic device capable of performing computations. It has many peripherals like a monitor and keyboard to accept or display data to users and memory to store information. But the heart of the computer is its processor, which does all the thinking for the computer. Coming back to our definition of computer, you may have noticed the keyword electronic. Thinking of it, if a computer is an electronic device, how can it understand and display text, images, videos, and other rich media information? Well, a computer understands only electronic signals, where a 5-volt current represents a binary 1 and a 0-volt current represents a binary 0. Your PC is continually bombarded with these electronic pulses, which it interprets. 8 bits of such signals are grouped together, and text, numerical, and symbols are identified by unique patterns of these 8 electric pulses. For example, the pound symbol is represented by the pattern 10101010. Instruction to add two numbers is represented by pattern 10000011. This is 8-bit computing. Current-day processors are capable of understanding and decoding 64 bits at a time. Suppose you were asked to write a program to add two numbers. Say add 1 with 2. Assembly language is the most elementary form of software development languages. Your code to add two numbers in this language would look like store number 1 at memory location, say A. Store number 2 at memory location, say B. Add contents of location A and B. Store results. The way you feed this code to the processor would depend on the PC you are using. Back in the 50s, when computers were huge and consumed a great deal of power, you would convert your assembly language code into corresponding machine code of ones and zeros using mapping sheets, and punch the machine code into punch cards, and then feed those punch cards to the computer. With advancement in technology, I/O devices were invented. You could directly type the program into the PC using a program called assembler, convert it into corresponding machine code, and feed that to your processor. That apart, you will also have to make calls to operating systems providing functions to display the output of code. With advancement in software development languages, this entire assembly code could be shrinked into just one line: print F 1 plus 2. A software called compiler is used to convert your C language code into assembly code, and the assembler converts it into corresponding machine code. Though present-day compilers come bundled with assembler, they can directly convert your higher language code into machine codes. Now, suppose Windows operating system is running on this Intel processor. Combination of operating system plus the processor is called the platform. The most common platform in the world is the Windows and Intel, called the Wintel platform. The other popular platforms are AMD and Linux, PowerPC, and Mac OS X. Now, with change in processors, the assembly instructions will change. For example, the add instruction in Intel may be called addition for AMD or math add for PowerPC. And obviously, with change in operating system, the level and nature OS level calls will also change. As a developer, I want my software program to work on all platforms available to maximize my revenues. So I would have to buy separate compilers which convert my printf command into the native machine code. But compilers come expensive, and there's a chance of compatibility issues. Enter Java language. The code to display addition of two numbers is system.out.println 1 plus 2, saved as a .java file. Using the Java compiler, the code is converted into an intermediate code called the bytecode. The outcome is a .class file. This code is not understood by any platform, but only a virtual platform called the Java Virtual Machine. This virtual machine resides in the RAM of your operating system. When the virtual machine is fed with this bytecode, it identifies the platform it is working on and converts the bytecode into the native machine code. In fact, while working on your PC or browsing a web, whenever you see either of these icons, be assured the Java Virtual Machine is loaded in your RAM. But what makes Java lucrative is that code, once compiled, can run not only on all PC platforms, but also mobiles or other electronic gadgets supporting Java. Hence, Java is a language as well as a platform. To understand the compiling process in Java, let's first take a quick look at the linking process in C. Suppose in the main, you have called two functions, f1 and f2. The main function is stored in a file a1.c. Function f1 is stored in a file a2.c. Function f2 is stored in a file a3.c. All these files are fed to the compiler, whose output is the corresponding object files, which is the machine code. The linker will club these three files together and produce an exe file. During program run, a loader program will load an exe into the RAM for execution. Let's look at the process for Java. In your main, you have two methods, f1 and f2. Main method is stored in file a1.java. f1 is stored in file a2.java. f2 is stored in file a3.java. The compiler will compile the three files and produce corresponding .class files, which consists of the bytecode. Unlike C, no linking is done. The JVM, Java Virtual Machine, resides on the RAM. During execution, using class loader, the class files are brought on the RAM. The bytecode is verified for any security breaches. Using the bytecode verifies of the JVM. Next, the execution engine will convert the bytecode into native machine code. This is just-in-time compiling. It is one of the main reasons why Java is comparatively slow. There is more to the JVM architecture, which will be discussed in later tutorials. Open Notepad. Declare a class with name A. Declare the main method public status void main string args. Type the system.out.println, which displays the text First Java Program. Save the file as firstprogram.java. Make sure to select all files while saving the file. In our working folder, a Java file is created. In a command prompt, make sure your current directory path is the same as where your Java file is stored. Enter javac firstprogram.java. This will compile the code. The code is showing error. The string is not declared correctly. Let's correct the error and save the file. Compile the code again. After making the changes in the string, the code is compiled successfully. If you look in your working folder, you can see that a file named a.class has been created. To execute the code, enter the command Java, followed by the class name. As expected, output first Java program is displayed. Now if you copy and paste the same code in IDE, like NetBeans, the compiling and execution is done on the click of a button. Using IDE is more convenient and can improve your efficiency, but since you are learning Java, we will stick to Notepad. Suppose you want to create banking software which will perform deposit and withdraw operations and show the balance. Let's examine how the software would be created using different programming languages. The earliest programming language were unstructured programming language. A very elementary code of the banking applications in unstructured programming language will have two variables for one account number and another for account balance. Suppose a deposit for $100 is made. Next, you will obviously show the latest account balance. Now the amount of $50 is withdrawn. Again, you show the latest account balance. In fact, for any further deposit or withdrawal operations, you would program the same steps again and again. Here the code for display of account number and account balance are exactly the same, and it is repeated throughout the program. Such repetition is a waste of programming efforts and increases coding costs and possibility of coding errors. With the advent of structured programming, common lines of your code were put in a structure called functions or methods. And wherever required, a simple call to their function was made. Now, if you can examine closely throughout the program, we are dealing with data or performing certain actions on the data. In fact, having data and performing operations on the data is the very basic characteristics of any software program. Thought leaders in software development came up with an idea to combine data and actions together. Hence the birth of object-oriented programming, commonly called OOPS. The same code in OOPS will have some data and the actions to be performed on that data. By this combining of data and action, we have several advantages over structured programming, namely abstraction, encapsulation, inheritance, and polymorphism. We will learn them in detail in succeeding tutorials. To understand the principle of abstraction, let's do an exercise. List the top 10 information like name, address, etc. of your customer to create a banking application. Pause the tutorial and complete the exercise. I'm sure you did a good job in identifying the information. Some of the information that will be useful would be full name, address, contact number, tax information, favorite food, favorite movie, favorite actor, favorite band, and I am sure you're wondering what the heck I'm talking about. Well, the amount of information available for you as an individual is infinite. We do not need all the available information for a customer to create a banking application, but only the relevant ones. In essence, we are selecting data from a larger pool, hence the name abstraction. But the same information once abstracted could be used in a wide range of applications. Like this data set can not only be used in banks, but will also be useful in employee databases, hospitals, government databases. The advantage is the same set of data can be reused. Coming back to the banking example that we used earlier, suppose a hacker is able to gain access to the code and tries to deposit an invalid amount into your account. Usually, variables in a class are set as private, and they can only be accessed via corresponding methods. So, such access is not allowed. Next, he tries to use the deposit method to carry out his operation. But the method implementation has checked for negative values and throws an error. Thus, you never expose your data to an external party, which makes your application secure. The entire code can be thought of as a capsule, and you can only communicate to it via messages. Hence the name Encapsulation. Consider the same banking application from previous examples. We're supposed to open two different account types, one for saving and another for checking, also known as current. Let's compare and study how we can approach coding from a structured and object-oriented programming perspective. In structure programming, I will create two functions, one to withdraw and another to deposit, since the working of these functions remains same across the accounts. While using the objects-oriented approach, we will create two classes, each having an implementation of deposits and withdrawal functions. This is redundant extra work. Now there's a change in requirement specifications for something that is so common in software industry. You're supposed to add functionality privilege banking account with overdraft facility. For a background, overdraft is that you can withdraw an amount more than the available balance in your account. Using functional approach, I would have to modify my withdraw function, which is already tested, and perhaps code a method like this one, which will take care of new requirements. Using OOPS approach, I just need to write a new class with unique implementation of withdrawal functions. I never touch the tested piece of code. What if the requirement changes further, like to add credit card account with its own unique requirement of deposits? Using structural approach, you have to change the tested piece of deposit code as well. But using object-oriented approach, you will just create a new class with its own unique implementation of deposit methods. So even though structural programming seems like an easy approach initially, OOPS wins in the long term. But one may argue that across all classes you have repeated pieces of code. To overcome this, you create a parent class, say account, and implement the same function of deposit and withdraw. And make child classes inherit account so that they will have access to withdraw and deposit functions in account class. The functions are not required individually. This is inheritance. But wait, there is a problem with the method of implementation for withdraw for privilege and deposit for credit card is different. To overcome this, you can override the method implementation in your base class, such that when withdrawn method for the savings account is called, this method is executed. But when withdraw method for the privilege account is called, the custom method is executed. This is polymorphism. Suppose you want to build software for a pet management system especially meant for dogs. Obviously, you need to store information about various breeds of dogs in your system. You need to model real-life entities, that is, dogs into software objects. And the million-dollar question is, how do you design such a software? First, let's do an exercise. You see the picture of 3 different kinds of dogs? Pause the tutorial and list down the differences between them. I hope you did a good job determining the differences. Some of those differences would be breed, size, age, color, etc. If you think for a minute, these differences also, in essence, are common characteristics shared by these dogs. They can form data members for your dog object. Next, identify common behavior among the dogs. Here's a hint. Eat, sleep, sit, and run. So we have identified actions for our software objects for dogs. Next, I will define the class dogs with the data members, such as size, age, etc., and with methods such as eat, sit, sleep, etc. And for different values of data members in my class, I will get different dog objects. You can design any OOPS program using this approach. Let's create a class account. With instance variables A and B. And a method setData to set the values for A and B. And a method showData to display the values for A and B. A main method wherein we create an object of account class. And call methods setData and showData. Let's compile and run the code. Our expected output, A and B, should be initialized to the values 2 and 3, respectively, but the value is 0. Why? Let's investigate. In the method setData, the arguments are declared with names A and B, while the instance variables are also named A and B. During execution, the compiler is confused whether A on the left side of the assigned operator is the instance variable or the local variable. Hence, it does not set the value of A when method setData is called. The problem can be overcome by this keyword. Append both A and B with the this keyword followed by a dot operator. During code execution, when your object calls method setData, the keyword this is replaced by the object's handler obj. Now the compiler knows the A on the left-hand side is the instance variable, whereas A on the right-hand side is the local variable. The variables are initialized correctly and expected output is shown. Suppose you are smart enough to choose different names for your instance variables and method arguments, but this time around you create two objects of the class, each calling the setData method. How will the compiler determine whether it is supposed to work on the instance variable of object 1 or object 2? Well, the compiler implicitly appends the instance variables with the this keyword, such that when object 1 is calling a setData method, instance variables are appended by its reference variable. While object 2 is calling the setData method, instance variables of object 2 are modified. This process is taken care of by the compiler itself, and you do not need to append this keyword explicitly unless there is some exceptional situation, as in our earlier examples. Consider that some line of your code is calling method M1. In the stack, a frame will be created from method M1. The variable x in M1 will also be created in a frame for M1 in the stack. M1 is calling method M2. In the stack, a new frame will be created for M2 on top of the frame M1. Variable b and c will also be created in the frame M2 in the stack. Say method M2 is calling method M3. Again, a frame M3 is created on the top of the stack. M3 is creating an object for a class account, which has two instance variables, p and q. The new operator will create an object in a heap. The reference variable ref will be created in a stack. The assignment operator will make a reference variable to point to the object in the heap. Once the method has completed its execution, the flow of control will go back to the calling method, which in this case is M2. The stack from method M3 will be flushed out. Since the reference variable will no longer be pointing to the object in the heap, it will be eligible for garbage collection. Once M2 has completed its execution, it will be popped out of the stack, and all its variables will be flushed, and it will no longer be available for use. Likewise for method M1. Eventually, the flow of control will return to the start point of the program, which usually is the main method. Consider the following scenario. The class Media Player. Media Player has two subclasses, CD Player and DVD Player, each having its own implementation of Play method. Another class, Combo Drive, is inheriting both CD and DVD. Which Play method should it inherit? This can cause a serious design issue, and hence Java does not allow multiple inheritance. But suppose you have requirements where your class Dog is inheriting class Animal and class Pet. But you cannot extend two classes in Java. So what would you do? The solution is interface. An interface is 100% abstract class and has only abstract methods. A class can implement any number of interfaces. Class Dog can extend to class Animal and implement interface Pet. Let's create class C1. With method M1. And a main method. Create an object of C1. and call method M1. Now let's say I want to put this class into the package. At the first line of code, write the statement package P1. Save file as demo.java. Let's compile the file. Compilation is done in a class file created, but we have to create a package for this. Use command javac-d.demo.java. This command forces the compiler to create a package. Here, dot operator means the current working directory. If you check out the folder, a package P1 is created, which has class C1. If you compile the same file with double dots, the package will be created in the parent directory, which is the C drive. Let's say you want to create a sub-package. Modify the statement as p1.p2. Compile the file. In your P1 folder, another folder, P2, is created with class C1. To execute the code, mention the fully qualified name of the class, that is, package name and subpackage name followed by the class name. There are two types of errors: compile time and runtime. Compile time errors could be again classified into two types: syntax errors. For example, instead of declaring a variable integer int a, you mistakenly declare it as in a, for which the compiler will throw an error. Or you can have a semantic error, where you have declared a variable int a, and after some lines of code, you again declare an integer as int a. All these errors are highlighted when you compile your code. A runtime error is called an exception error and is any event that interrupts normal flow of program execution. Suppose you have coded a program to access a server and things work fine while you are developing the code. During the actual production run, the server is down. And when your program tries to access it, an exception is raised. If you observe, these are not any syntax or semantic errors, but arise due to situation out of the developer's control. For example, the programmer would never know a server's downtime beforehand. But blaming your code failure on environmental issues is not a solution. You need robust programming which takes care of exceptional situations. Such code is known as exception handlers. In our example, good exception handling would be, when the server is down, connect to the backup server or mirror server. To implement this, enter your code to connect to the server. You will check if the server is down. If yes, write the code to connect to the backup server. Such organization of code using if and else loops is not effective when your code has multiple exceptions to handle. Hence, Java provides for inbuilt exception handling, where normal code goes into the try block and exception handling code goes into the catch block. Try block will contain code to connect to the server, and catch block will contain the code to connect to the backup server. In case the server is up, the code in the catch block will be ignored. In case the server is down, an exception is raised, and the code in the catch block will be executed.